Our focus today will be on thoroughly exploring and understanding the final two distinct estimation methodologies that are specifically applied within the realm of univariate analyses, particularly for the purpose of time series estimations. As a reminder, don't forget that our website also has a YouTube channel with all the videos we've made so far. The last two videos discuss the ARIMA and seasonal ARIMA model. Today we will be discussing a straightforward extension to the ARIMA model and its seasonal counterpart. We are going to incorporate the letter X. In this particular case, we will be maintaining the exact same notation and the underlying mathematical concept. However, we will also be accounting for an additional external variable. This particular action represents the only additional step that we are obligated to perform, and subsequently we shall proceed to make use of the identical illustrative case study that we had previously presented, which involves the Microsoft Sales Growth Time Series numerical data. Just to give you a quick recap and overview of the ARIMA and the seasonal ARIMA model, let's consider an example. In this mathematical model, we'll include two autoregressive components. Those autoregressive sections will precisely determine the quantity of previous or lagged values that are used to predict the current observation. So, for instance, the sales growth figure might exhibit a certain momentum as time progresses, meaning its current performance is often dependent on the preceding 1, 2, or even 3 historical data points. The second part of this analysis is the moving average, and that specifically relates to the various shocks, or more precisely, the model error. This suggests that if we develop new innovations, particularly those that are completely unforeseen, they possibly could have a significant impact on the current trajectory of sales growth. The AD component is crucial here, particularly when we're analyzing original data that displays non-stationary properties. In such specific scenarios, it becomes absolutely necessary for us to apply the first difference transformation to ensure proper analysis. And if it becomes necessary, if the initial difference is not quite sufficient, then we must increase that to 2 or even 3. However, in many common scenarios, simply observing the initial difference can often be quite sufficient, and the significant new variable that we are now going to incorporate into our detailed analysis is specifically the exogenous variable x, which is precisely why it has been designated as x in this particular context. So after we've taken the first difference, so we're dealing with a stationary variable in this case, and its first difference will effectively remove any underlying trend. And just to quickly refresh your memory, let's review the definition of what makes something stationary. Since our current focus is on the topic of time series, let's use the notation xt as an illustration. In this particular case, the variable t clearly signifies the distinct periods or intervals within our dataset. If for some reason the main parameter of the variable x, whether it's the mean, the variance, or the autocorrelation between the values, if these parameters are indeed a function of the specific location of time, denoted as t, then this inherently means that we do not possess stationarity in their observed values, primarily because their very nature and magnitude are directly dependent on that particular temporal position. So, in this specific instance, the values for these parameters will be quite distinct from this particular point in time. So, whenever the actual parameters or the entire statistical distribution of our particular variable, it's a direct consequence of the passage of time, not simply a fixed duration. This clearly indicates a fundamental lack of stationarity, and we absolutely must address this critical issue before proceeding with any further analysis, especially before we attempt to fit any statistical model to this data. So, before we examine the autocorrelation chart or apply the ARIMA, ARIMA, or seasonal ARIMA models, we first need to ensure that the data is stationary, meaning it does not depend on the exact point in time. So as you can see, here we have a simple ARIMA X model. This is a difference variable, which means we're dealing with a stationary time series. Pause. This particular variable is essentially a function of its own past values. Specifically, the autoregressive AR term, pause, is derived from the lagged version of this very same variable, indicating its dependence on prior observations. And we can confidently state that 2 lags are indeed enough to fully capture the momentum movements of this particular variable. We also introduce an exogenous variable, OX for example, which could specifically represent the overall sales growth of the particular industry where the focal firm is operating. And what we're discussing now are the specific moving average components, which represent the sudden innovations or the unexpected error shocks that are projected to carry their influence and effects over into the immediate short-term future. So, whenever we experience a short-term correction, it's important to remember that these lagged errors will undoubtedly have a significant impact on the current value of our variable of interest. The seasonal ARIMA X model in its fundamental structure is precisely the same as the regular ARIMA model. Key difference is that we will be introducing a seasonal component. Seasonal describes the regular recurrence of events or patterns tied to specific calendar periods. For example, if S equals 4, this indicates that every 4 periods or cycles, a particular event or condition will repeat itself. We are going to experience some truly unique and special movements. Considering the specific nature of that particular level, and indeed of that variable itself, it becomes quite clear that the prevailing season will inevitably have a substantial impact on the current observed level of our variable. To illustrate, the performance of this current quarter is often heavily influenced by how the same quarter performed in the previous year. For instance, it's quite possible that we could experience an unusually high demand for a particular product during the month of January, or perhaps throughout the entire first quarter of the fiscal year. So, the current season, which is the first quarter of the calendar year, is indeed a significant factor, and we effectively manage this by incorporating the variable S. For example, the seasonal ARIMAX model would be constructed in a fashion similar to this. We are considering the autoregressive model and also the significant seasonal impact that we observe. And at this stage, it is absolutely crucial that we proceed to remove the undesired interaction effect. The reason for this observation is that the yt-1 variable is significantly affected and partially controlled by the yt-5 variable, primarily due to the seasoning effect. Similarly, the variable at time t-4, which included the seasonal effect, is also partially influenced by the variable at time t-5, given the autoregressive structure. Given that we are operating within an AR2 framework, this signifies that the lag term of yt at the -4 position will subsequently be established and directly influenced by the yt at -5, and it is quite conceivable that we might also include yt at -6 for this specific instance. So that will remove the interaction effect because the influence of yt-5 is actually present in both of these locations, embedded within them. Therefore, in order to completely eliminate that, we must subtract the interaction effect. Then moving on, we encounter the exogenous component. This is crucial because in our current analysis, we're specifically working with the X variable within the framework of a seasonal ARIMAX model. What we're observing right now, this particular output represents the residual error that results from the process of fitting this specific model to our data. Our ultimate objective and what we are truly hoping for is to achieve a perfect zero value for this error term. This implies a complete absence of variance, meaning there is absolutely no error present, unlike typical models, where we often encounter a degree of variability in the And then we have the MA shocks, which are essentially the error terms derived from previous observations. And then, in addition to those, we also need to consider the seasonal MA shocks. It's important not to forget the seasonal effect. The abnormal movement is composed of two distinct parts. First, the lagging component similar to an AR part, and secondly, the innovation component. Once we have completed the fitting of this model, we then proceed to apply the seasonal ARIMAX. So, this particular one appears to be the most complex of all, primarily because we are introducing far too many variables into the overall system, and we are going to apply that using. To illustrate this concept, we'll take an example of sales growth for a particular firm. Just as we did in our previous video, we'll use Microsoft as our example. So I'm going to select the quarterly data. I'm currently navigating the Finance ResearchGate website where we can find this information. And then we must ensure that we select the complete time duration, and then we can apply it. Within the Series A classification, we will now proceed to select sales growth. This particular metric is formally defined as the percentage change in the company's total revenue when compared to the immediately preceding financial quarter. So, what we're discussing here is the change in our overall sales performance, specifically when compared to the previous 3-month period, presented as a clear percentage.
First, we need to locate and search for the specific stock ticker symbol associated with Microsoft. Once that ticker is entered into the designated input field, we will then proceed to press the Enter key. Following that, it's important to move our cursor and perform a click somewhere outside of the active input box. This final action is crucial to ensure that the system properly registers and displays the results of our search query. First, we will select the specific company, which is MSFT, and then we will proceed to apply. This means we're applying the chosen variable, the relevant metric, exclusively to just one firm, and subsequently, we are retrieving all of the necessary data. So, then, we will have all the essential data points ready for Microsoft. Following that, we must also create the crucial exogenous factor, and we will proceed to apply the projected sales growth rate that is relevant for the entire industry where Microsoft is positioned. So I'm going to create another series. Of course, I will be selecting the exact same variable that we are interested in for this particular study. And incidentally, the exogenous variable, meaning one that comes from outside our system, can be any other relevant factor. In our particular situation, this specific variable will be the overall growth rate of industry sales. Here, we will proceed to select the industry sector where Microsoft is correctly placed. That is, naturally, technology. And then we will apply it. You can easily confirm that Microsoft is present right here. If you scroll down a little bit, we should definitely be able to locate Microsoft's operations within this particular industry. By scrolling down, we can clearly see the visual representation, the chart for both of these data sets. The first one, labeled A, represents the data for Microsoft, and you have the option to easily rename these series if you navigate to the section located just above. For instance, you could select this specific point here, which is currently designated as Series B, and then you would be able to assign a new name to it, like
Technology sector sales growth.
And you can apply that same approach to Microsoft, particularly when it comes to their sales figures.
Growth micro.
All right, if we navigate down a bit further on this particular screen, we'll then be able to precisely select the newly designated variable, which is Microsoft sales growth, and the overall sales growth within the sector. And so here we have the variable we're examining. Now we've observed that there are some clear outliers present when we construct the technology sales growth. The main reason for this is that we specifically selected the mean, and consequently, we might have an outlier for just a few of these firms. This would inevitably lead to a significant distortion in the numerical value of that particular variable. Therefore, the most effective and appropriate method for us to consider when we are constructing the industry level variable. So, our best course of action is to select the median. The median, you see, will be considerably less exposed to the effect of any outlier. And we should implement this right away. And call it median. So, when we look at the overall performance, technology sector's median sales growth figure, I think, should be more than adequate for our purposes. Sure, we can clearly observe the sales growth trajectory of Microsoft when compared directly with the overall performance of the sector. It's quite evident that these two metrics appear to be strongly correlated with one another, and if you examine the specific correlation coefficient, you'll find it stands at approximately 0.45. Presence of such a strong correlation presents a very promising opportunity for us to effectively utilize the sector's growth rate as an exogenous variable within the framework of our analytical model. When we examine the data, specifically the count and the mean values presented here, it becomes clear that Microsoft's average sales growth stands at 4.16%, whereas the overall sector's growth rate is recorded at 3.44%. And to accurately determine the appropriate values for P and Q for the specific variable of interest that we are currently modeling, which, as we've discussed, represents the sales growth of Microsoft, you can then refer to the autocorrelation function, or ACF. And you can also figure out the seasons as well. We've discussed that in the video that was related to the seasonal ARIMA. Here, we've established a seasonal cycle of 4 precisely because in every 4 periods we consistently observe the highest autocorrelation coefficient. This significant pattern then repeats itself. To determine the optimal number of lags for our autoregressive model, we must carefully examine the behavior of the partial autocorrelation function. We can clearly observe that the PACF cuts off quite sharply after the very first lag. This strong indication suggests that an AR1 model will be perfectly sufficient.
In order to determine the value of Q, which represents the quantity of error shocks present within the MA model, we typically examine the autocorrelation function to see precisely where it effectively cuts off.
It doesn't really cut off at any specific or particular level, so the exact point isn't entirely clear. Therefore, let's also make sure to select just one in order to be consistent with AR. Since AR is currently set to 1, then if you were to go back here, for that particular component, that would represent a single term. And then regarding the MA term, we will also be considering just one term here. Similarly, when we look at the seasonal aspect, that will also constitute one term. And finally, we are going to incorporate a single term specifically for the MA shocks. This is specifically related to the seasonal impact that we've observed. Consequently, our proposed model will be less complex than this current model because this particular model is currently using 2 distinct autoregressive terms for the AR and also 2 separate terms for the MA shocks. However, in our specific case, we find that just one term is perfectly sufficient. So if you would please scroll down the page.
Regarding classical time series analysis, we've introduced a new feature here that allows you to construct a dummy variable. This is particularly useful in situations where we determine that a dummy variable could effectively be incorporated as an exogenous variable. For instance, we might choose to include a dummy variable to represent a crisis, such as the recent global financial crisis. This can be incorporated quite easily. Alternatively, you have the option to choose any other relevant variable and then proceed to create a corresponding dummy variable.
For the specific situation we're discussing here, we've decided to incorporate the overall industry's sales expansion as what we call an exogenous driving factor, and our primary objective is to create a model that predicts the future sales growth trajectory for Microsoft.
And we can now simply leave this particular matter as it stands.
If you want to rename the residuals, you are free to do so. Here, the exogenous variables are exclusively used for the ARIMA X in the season ARIMA X. We know this, so we must proceed to select our model.
Let's start with the ARIMA X and discuss its initial specifications.
You just need to give it some time.
So we determined that the autoregressive component is 1 and the moving average is also 1. The crucial question now is, do we actually need to difference this particular variable? We should definitely check that. So we've applied the augmented Dickey-Fuller test and also the Philip-Perron test. And what we've observed from these tests is that both the y variable and the x variable, they are indeed stationary. This indicates that we are ready to proceed, and there's no need to apply any differencing, since the p-value is statistically significant. This holds true for other tests as well. For instance, the Philip-Perron test is also significant, therefore differencing is not required, because the specific variable we are currently analyzing is not representing the actual level of sales. If we examine the level of sales, for example, it's quite likely we're going to observe a trend, and that will not be stationary. Therefore, we must apply at least the first difference.
This variable is already quite different, because it's the actual sales growth.
What this essentially means is that we first determine the numerical difference between the total sales volume generated in the current reporting cycle and the sales volume from the immediately preceding period, which we define as the last fiscal quarter. We then proceed to scale that resulting difference by dividing it by the total value of the sales from that same previous quarter. Okay, so I'll go down here.
The difference in our case is 0, and then we can fit the model.
Here, our exogenous variable has been found to be statistically significant, and this is a very positive and encouraging outcome for our model. Furthermore, if you then turn your attention to the autoregressive component,
It is not significant.
it's important to note that the MA aspect is quite significant. So if you go beyond this point, this particular value, as you can see, is not statistically significant. Therefore, the phi coefficient that we are looking at right here is indeed this specific value. Consequently, we do not possess a coefficient value for the second leg of our analysis, primarily because we have exclusively chosen to include just one leg, specifically this particular one and no other. And for the next part of our discussion,
So, regarding the MA shocks, the coefficient for theta, specifically this one that we're observing, is found to be exactly negative 0.4655, and this particular finding is indeed statistically significant. This indicates that if we were to see a revision in the figures from the most recent reporting period, it would then lead to a noticeable decline in the overall sales growth performance of Microsoft. Now, the term sigma specifically represents the statistical variance of the error term, and understanding this value will provide you with a clear indication of the magnitude or the extent of that error.
Our primary objective is to achieve the absolute lowest possible sigma value. Therefore, if you proceed to calculate the square root of this particular number, the result will directly provide you with the standard deviation.
The error was in being one step ahead.
So if you take the square root of this specific value, that will then give you the total amount of the error.
Here, we can thoroughly check to see if there's any autocorrelation present within the error term. This is important, especially if our model is effectively capturing both the seasonality and the underlying dynamics. That shouldn't be considered a significant factor, and this is precisely what we find with the ARIMA model. If we examine the chart presented here, you'll see the actual values compared to the fitted predictions. It's performing quite well overall, and that's due to the fact that the autocorrelation of the residual is not showing any statistical significance, meaning that we successfully modeled the autocorrelation of our variable of interest, because the error, that is the part that we couldn't model, is not significant when it comes to the autocorrelation. This is a very positive indicator for the overall strength and reliability of our model. The presence of heteroscedasticity will specifically indicate whether the variance of the error terms is fluctuating or changing across different observations over time. And indeed, we are observing that it is. The volatility of the error is clearly undergoing a change. For example, at this point here, we are experiencing a high error. However, in the subsequent period, we are observing a low error. This pattern is consistently changing over time. It's important to note that we are not attempting to model the inherent variability of the variable. Instead, our primary objective is to model the average dynamics of the overall model, and consequently, it is quite natural to observe some degree of volatility within the residuals. If we want to model the volatility as well, then we have different separate models that we can discuss in other videos. Now, if you were to proceed and execute the seasonal ARIMA model, that would be the most appropriate course of action. Wouldn't you say, Max? I'm going to retain our target variable, along with the exogenous factors. Next, we introduce the seasonal term into our model. As we previously discussed and agreed upon, we'll use a single term to represent this seasonal component. This is because the seasonal pattern consistently repeats itself every 4 distinct periods. This unusual fluctuation, occurring every 4 periods, is composed of 2 distinct elements, specifically an autoregressive AR component and a moving average MA component. So, beyond just the autoregressive component, we also find an autoregression that incorporates the MA shocks within the seasonal movement itself. As is well known, there's no need to difference this variable. Given that our variable of interest is already stationary, there's simply no requirement for differencing.
Then we can fit the model.
In this case, our exogenous variable is statistically significant because its p-value is below the 5% threshold.
The AAR term is important to recognize that each one carries substantial significance, whether we're discussing the standard autoregressive and moving average terms or the distinct seasonal component.
Now, if you carefully observe the sigma value, you'll notice that it is significantly less than the value we previously obtained from the standard ARIMA model. This clearly indicates that the seasonal ARIMA model has effectively lowered the overall amount of prediction error. Let's take a look at the chart right here. It appears this model is effectively capturing the seasonality, because it is simply capturing the essence of what we're trying to achieve. That we're talking about a fluctuation that is clearly due to the time of year, the season. But the one crucial aspect that this particular model isn't quite able to capture is the overall magnitude, the complete extent of that entire fluctuation, and that specifically includes the seasonal component.
Well, that particular aspect might very well be the sole remaining element that we need to focus on for improvement. However, when we consider all other factors, especially those pertaining to the crucial concept of autocorrelation, this, in fact, represents the most critically important component, and it absolutely must not show any statistical significance. This means the error's autocorrelation is no longer significant because we successfully captured that autocorrelation, which was our main objective for the primary variable. We achieved this because the residuals now clearly show no significant autocorrelation. That is certainly the most important piece of information that we have to consider. We've observed that the variance of the error term is actually changing, and this is something we previously discussed. This is quite normal and expected, primarily because our model did not explicitly account for the inherent variability of the underlying variable itself. Instead, our focus was solely on modeling the average or mean dynamics of that particular variable. To be clear, we concentrated on the mean dynamics, not its inherent variability. What we're looking at here are the specific values for the skewness and the kurtosis of the residuals.
This isn't too far from what we consider normal, because a normal distribution typically has three important characteristics. For instance, the skewness of a truly normal variable is always exactly zero. A positive skewness, however, indicates that we're observing movements with a rightward tilt in the error distribution.
What this implies is that after we have successfully fitted the model, the observed error values are predominantly positive rather than negative. This particular characteristic is precisely what accounts for the presence of a positive skewness in our data.
So, if we fit a model, we likely understate the true value, and that's evident here because
So the error term, when we look at the positive deviations, for example, like this, and this, tends to be, on average, significantly higher compared to the errors observed on the negative or downward side. And so that concludes our presentation for today. I want to express my gratitude to all of you for listening.